CodeFusion. It's a paper made by Microsoft, and it introduces a cool idea where you basically generate code using a diffusion model as opposed to an LM, but it also introduces the cool idea that GPT 3.5 Turbo is 20 billion parameters, which it seems, I'm not going to make any crazy claims, but it seems like they're trying to hide that after they release this paper. So that's something interesting. It is the first time there's a kind of official release on the parameter count of the model, GPT 3.5 Turbo, which is what runs ChatGPT. So interesting. 20 billion parameters, much less than what people thought, because 175 billion parameters was the original GPT-3 model. So if it's 20 billion parameters, then that would be kind of crazy because it's really good. And we're like, Llama 60 billion parameters is close to ChatGPT. But if ChatGPT is only 20 billion, that shows that there's a large margin between open source and ChatGPT. So very interesting. But yeah, that's an important thing this paper brought about that may or may not be true. They said that they got this from an article, but since these people work at Microsoft, it kind of seems like that isn't true. But anyways, enough of the ChatGPT size stuff. We will see if that's true. The paper itself is actually really interesting. So a normal diffusion model, I will show how normal diffusion works on images like usual, and then translate that to text. So a normal diffusion model, like always, is you have your picture, like so, and this is your picture at x times 0. And what you do is you have this function, which we will call, say, q. Q is what they did in the original DDPM paper, so we'll call this q. And this adds a little bit of noise, so this will be time is equal to 0, this will be time is equal to 1, and this will be x1, and you add a little bit of noise to that. Move this over a bit. And then what you do is you add a little bit more noise to this image. So you send this through the same function q, or you have some noise scheduler function q, and this will give you x2 at time is equal to 2, and it's a little bit more noisy. And you keep doing this over and over and over again until you get to a final image, which is just pure Gaussian noise. So this right here is pure Gaussian noise. And this is t is equal to big T, x big T. In the original DDPM paper, this was 1,000 steps. So you basically had this discrete Markov chain where that was 1,000 steps long, basically. Now, what you do, or you can actually get anywhere in that chain using a function similar to this. It's similar, it gives you the right idea. It is not this function, but it's similar. So big T minus T, and you can normalize this, x0 plus big T, or little t, z, where z is sampled from a normal distribution, or they use epsilon. So epsilon is sampled from a Gaussian. So this function here basically allows you to go anywhere in the process here. So whenever t is equal to 0, then you have 100% x0. And whenever t is equal to big T, then you have 100% noise, and you can interpolate anywhere in between there. So that's how you can basically like skip anywhere. Because Gaussians are nice, you can basically skip anywhere in this process in one step, as opposed to continuing down the chain to get your image at any step. You then use a function which we'll call, say, q theta, and this function is going to be our model. This is going to be the learned function. And what q theta does is it basically predicts the noise in the image. So q theta, it basically predicts the noise in the image, and you can remove that noise to give you the previous time step. So let's say we have this image here. that one. So we throw this through our model, Q theta, like this. We also throw the time step through, and it'll give us the noise. So if I paste this over here, and I remove the cat, basically it's trying to learn how to remove the cat, which is a deterministic process. It's not random. Then you get the noise out, and you can basically subtract the noise to give you the picture of the cat. And you do this for a bunch of images, and it learns this probabilistic this distribution, and it can basically predict the noise at any time step. And you give it the final time step, you let it do predictions on that, and it basically reverses the chain one step at a time. You can skip steps and stuff, but that degrades basically how good the quality is. It's a trade-off, speed versus quality. Now, Stable Diffusion stuff keeps this continuous, so this actually uses an SDE in Stable Diffusion. But in this paper, it looks like they don't make this a continuous process, which is kind of strange. Um, Modeling it as an SDE and an ODE is much more powerful, but in this paper, they model it exactly this way. They model it as the DDPM paper, where you have a discrete chain and you only have a certain number of steps. I think they use 1200, so it is 1200. Now, of course, we're not doing stuff with images, we're doing stuff with text. So what is the text equivalent? Well, this is very easy to translate. So if you have a sequence, maybe the cat sat. Yes, good old sentence. You have this sequence, it's in some embedding space, which we'll get to how they embed that later. But imagine you have this token sequence that is of shape n by d. So basically each token is of shape d. And it's in a continuous space. So note that we can't just have a vector that's 1, 0, 0, 0, 0, 0. We can't just have a one-hot vector. This has to be in a continuous domain with some continuous values. So this x0 is in R. It's not in Z. It's not in the integer domain. So, I mean, it's pretty easy to visualize how you would noise this. You would just add noise using a function q. And basically each of these tokens is corrupted into noise. So I will show that by putting red dots here. But in reality, you're just adding Gaussian noise to an embedding space, and it doesn't visually look like anything. So this would be, it's x0. This would be x1. And then you keep doing that over and over again, and you eventually get here, where these tokens right here, it's all noise. This would be x sub t, x sub big T. And big T is equal to 1200, I'm pretty sure. I think it's 1200. Let me check. 1200. Okay. So it's a discrete process like we visualized above. And then you just train a model to reverse this. So if this was P, then you train a model Q. Q theta. You train a model Q theta to reverse this. I think I messed that up. This is actually supposed to be P, but you get the idea. Basically, you have a function that noises it going forward, and you have a learned function going backwards to denoise it. And this is just going to be some continuous token representation, and you just train a model to reverse this. Now, this uses a UNet, because a UNet is good at images. What do you think this uses? Obviously, a transformer, but it doesn't just use one transformer, it uses 3 transformers, 3 times the power. So they use 3 transformers for this to do this modeling process. So let me show you the entire training pipeline for this. Basically, they have a strange setup. So, and it seems like they copy it from a paper called Genie. They mention it often. Genie, right here, right there. And it seems like they almost like copy it and change a few things, and then they do it, put it on code, and it works really well. So that's interesting. But yeah, so this is the model here. Now I'm going to draw a picture out to kind of show how it works in total. So basically, we have you basically want to say you want it to model code. So to have it model code, it's going to be predicting code. So this denoising part here, that is going to be our, that's going to be this part here. That's going to basically be our queue, this denoiser. But they also have some other parts to it. And this denoiser is going to be what produces our code. So these tokens here, the cat sat, maybe that would be like print hello world. So maybe we would model this as like print, and then you have, we'll do this in Python. Maybe that's a token, and then hello world, and then that. So maybe each of these is a token in some space. So this will be our original representation, and this will be a one-hot representation. So this would be of size v, and this would be n. So n by v. One-hot encoding representation, the usual. So this would be like 1 0 0 0 0 0 1 0 0 0 0 0 1 0. Well, to kind of change it up, 0 0 0 0 1, and so on. Whatever. It's whatever your vocab size is, you do a one-hot encoding vector. So then what you do is you send this through a layer, which they call L, and this is basically just a lookup table. So for each of, basically you send this through a matrix of shape. It would be V by E, and you just multiply each of these vectors by this, and you get out the corresponding embedding vector. So basically you're translating this from a discrete space to a continuous space so that you can actually do the noising process on here. So you send this through a linear layer. It's just a linear layer. It's always a linear layer, and you get out your let me draw it over here like that. You get out your embeddings, which are of shape n by d. N by d. So you just embed these, and this is going to be our x0. So you have your one-hot vectors for your code. This is the code you want it to generate, and you basically send this through a linear layer, and then you get out your embeddings. And this is still for each vector. It's just drawing it as a block. So then what you do is this will be your noising process. This will be Q. So we add some noise according to this function up here, or not this function, but a similar function to this, the same idea for that function, according to some noise scheduler. They use like a root scheduler, one of the schedulers for diffusion. And you get out your noisy embeddings at time t. So these are our original embeddings, the ones we want to denoise to, and these are our noisy embeddings. So yeah, I'll just draw some red here, show it's like a little noisy. So this can be anywhere in our chain, and we basically sample this randomly. You then have your diffusion model, which they call the denoiser. So this will be our diffusion model, which is n, and this is just a transformer. So you just send this through a transformer, and you get out some corresponding noise prediction. So this will be noise prediction, epsilon hat. Yeah, so this is our noise prediction, and basically, yes, this adds noise epsilon at time t, and we basically want to predict the noise. So if this adds noise epsilon t, then we want the model to predict epsilon t, this model here. And that allows us to remove the noise from the code embeddings to give us our embedding. So this is our first loss. This is just MSE between the predicted and the actual noise. And if you just have this, you have a diffusion model that can theoretically take some noise and just reverse the process and then produce some code. It's not very useful, but you can. So they add an encoder here to make it more useful. Encoder. And this encoder Yeah, these are embeddings for the encoder. But this encoder basically is a transformer, and you can use, in this case, it's T5. If you know the model T5. If not, you probably have heard of the model BERT, and it's similar to BERT in a way. Basically, you're just encoding text in some way. So maybe this text says, "Write me hello world" in Python. So basically, you just encode this text using some T5, or you're using a T5 encoder, and you get out a matrix of shape n by d. So basically, you have m vectors representing this text, and it's in embedding space d. So you actually condition your diffusion model on this. So and you can just do that by cross attention. So this is just your cross attention conditioning. So now what we have is we have a model that generates code based off a text description. They also do a second task, and the second task is maybe you're given like a lot of code. Maybe you're given like, I don't know, you have some class here. The class does some things, and maybe you have, well, the class has some functions, and maybe you have some function here, and I don't know, you want a class do something, or function do something, and you're like, I don't know what this should be. And then you put this through the model, and the model denoises this. They call this, it was CPD. This was originally for text, so basically you would have a whole document, and then you would mask a middle part of it, and it would try to predict that. Basically, you're doing the same thing here. So it tries to predict this part here, which is what the output code would be. It would be that part here. So there's two tasks. It's given some text, generate some code, and given some code, generate some code that's masked out. So those are the two tasks. So at this moment, we currently have a diffusion model that should work pretty well. However, there's they do an extra decoder part. So this part here is good enough, but what they kind of think is that these embeddings, they don't exactly have, like, it's hard for them to form relationships because you're just sending it through the diffusion model, and the diffusion model is just predicting noise. But what if the output tokens, before they are sent through a linear layer to make the predictions over here, they may need to find some relationships among each other before they give the output probability distributions. So from e hat, we can essentially get a x hat 0. So this is our prediction for the original embeddings. This would just be of shape n by d. Now, the Genie paper basically said, the Genie paper was for text, but they basically, from what I know, is they basically modeled two losses. So it was the noise loss and then this loss here, where this loss was between, they also modeled a third loss, but these two losses, basically it's saying you have a reconstruction loss and a noise prediction loss. However, this paper does something interesting with the second loss. So they basically have this decoder here, and this decoder takes the outputs here. So it takes the predicted outputs, and it's also conditioned on the text encoding, so the text instructions. And it basically predicts something called DS. And since this is also a transformer here, you get out a shape, this is n by d, you get out a shape that is also n by d. And instead of the loss being between these two, you basically have a loss between these two here. So this would be loss 2. So you don't have a reconstruction loss, rather you send it through a decoder, which then forms relationships among the tokens that are non-noisy. I guess it kind of like corrects this matrix here. And that is the output. So instead of it just being the direct output from the diffusion model, which may not be super good, you send it through this decoder to find relationships among all the tokens, and then those are your final embeddings. You then send this through a function h, So this is just some linear layer basically, and for each token, it'll output a y hat. So it outputs y hat total, and this will be the prediction for, say, print. So maybe this will give you your distribution. Hopefully it looks something like this, where this is the print token. And then it gives you one for the second token. Hopefully it looks like that. And the third token and the fourth token and so on. So you get these probability outputs, and your final loss is the negative log likelihood of this, just normal training. So the negative log likelihood of these, like cross entropy, basically. And these losses are right here. So if we look here, you have this first loss, which is the noise prediction loss. That's right here. And the noise prediction loss basically trains the diffusion model. You can see the gradient flow that way. The denoising, or the reconstruction loss, basically trains the decoder. I don't think they train the diffusion model on that. And then this final part basically trains the decoder. This loss here trains the decoder and H is your final projection. Now our function L is also learned, but that's thrown away because you are basically going to start from this here and then do the process this way. So this is just here for training. You aren't going to actually use that whenever you're making a prediction. Another note to make is that they have that here. I'll get my highlighter. They say both pre-training and fine-tuning tasks use LT, so use the loss function up there, because there is no natural language utterances in pre-training. There is no input ES to the denoiser N. So they basically have two parts. They have pre-training, and pre-training basically only has code. So you don't have this part here. It only has code. So you're just training this model on a ton of code, so it knows about code. And it doesn't know ES. So that's the initial part. It's just pre-training on a ton of code and having this diffusion model learn how to generate code, having this decoder also learn how to generate code. And then it says in the unsupervised code generation task, ES is replaced by Gaussian noise. So this is just Gaussian noise right here. And at every denoising step, and then the CPD task, every ES is computing by passing the masked code through the encoder. So basically this part isn't really used, this encoder part isn't used until you do the fine-tuning part. So you basically train it on a bunch of code and then you fine-tune it on to kind of make it more chatty in a way, to make it more responsive to the user. So yeah, that is the model. It's a pretty cool idea how they take the noise through a diffusion model. And I don't know, just the way they train it, it's pretty interesting, and it's interesting how well it works. So that's the model. All three losses. I'm pretty sure this L2 loss is this. I could be mistaken by what they said, but I'm pretty sure it is this part here. That would make the most sense to me. They kind of talk about it in a weird way. Yeah, okay. So that's the model. And you do the pre-training, you do the fine-tuning, and then you finally have this. You have this model that can generate code given a text prompt or given the other continuous paragraph denoising prompt. And once you have that, then you can generate some code. So let's see some of the results from this. So yeah, if we look here at which one wins. So this is baselines on natural language to code generation for Python, Bash, and CF rules. I don't know what CF rules are. If you do, then cool. You know why this does better, but I'm guessing that's why GPT-3 is worse at it, because maybe it's not as known. I don't know what those are. But if we look at Python, if you do a top one prediction, so you just take the first prediction, then GPT-3 wins. But if you do more sampling, then CodeFusion wins. Same with Code T5 code T5 for bash wins for top one. But if you do multiple samples, then CodeFusion wins, and then the same for CF rule. Well, CF rule just wins across, but so overall it does pretty good. One of the biggest things is the parameter count. So this only has 75 million parameters, which is very small compared to these models, like 175 billion. The GP3 is general pre-trained, so you can't really knock it for that. But like Code T5, that's like 10 times larger, and it's not as good. So this model is really small, and it's beating all the benchmarks. So it's really small, and it beats everything. So that's really cool to see. According to their results, I don't know how accurate those are. I don't think that they didn't open source this. So yeah, so this is diversity. It does the best on diversity, it looks like. According to these metrics, they say comparison of diversity in the top 5 code generations. For those languages, we report fraction of distant token level n-grams, pairwise similarities of code BERT embeddings of outputs, and statistics over pairwise string normalized edit distance of output. So they basically have some metrics for diversity. And then syntactically correctness, that's very important. And it is much more syntactically correct for the languages for these 3 models. I don't know why they didn't have the other models in here. But yeah, it's much more, it's pretty good for syntax. And this is just top 1 generations. So it's not multiple outputs, it's just one. Yeah, so another interesting thing is if we look here, this is kind of an example of the generation. Basically, this is the natural language input. So this is after you fine tune it. You have this input that says copy the content of file.txt to file2.txt. And I'm guessing this is in Python. And yeah, that's the target. That's what you want it to predict. And you can see at time step 1200, so this is just pure noise. It is pure noise. And whenever you decode that, it's just going to be noisy. If you just do 200, I think, oh, this is excessive. So after 200 steps, it does better. And yeah, it keeps on getting better, obviously, because the more time steps you do, the closer it gets to the actual number of time steps it was trained on. So after 1200 time steps, it looks pretty good. But the denoising process here is kind of interesting to look at. Going because it's in like text form, and you don't really see that for diffusion models. So this is interesting. How it goes from, as you would expect, noise from noise to not noise. They also have another example down here of a failure. So yeah, this is just another example. Remove directory tree folder name, and you want it to use shutil to remove the entire tree, and it picked OS removedr. But it's interesting because OS removedr is like similar, but it only does it if it's empty. shutil will completely remove it. So it's interesting that it picked something similar, but not quite right. So it almost got it. And it also forgot an S here. So it's interesting that it almost got it, the diffusion model, but not exactly. And it's weird. It's kind of weird looking at this in a diffusion model aspect as opposed to a language model aspect, because it's doing this in one shot. It's sending this through a transformer all together, all the text. So it's not going to predict this word and then this word and then this word. It predicts all this at the same time. So it's interesting to see that. So that's a failure part, and they show it requires like 1,000 steps in order to do well. So if you've used diffusion models, that's pretty slow. I think this can be a lot better if they make a continuous process with stochastic differentials and ordinary differentials. I don't know why they didn't do that. They just used normal DDPM. Yeah, they used the Markov process. And it's a lot better if you make this a continuous process. All the stable diffusion models, those are all continuous. Those are all stochastics, and you solve it using an ordinary differential equation. And that's why you can take 35 steps as opposed to 1,000 steps to generate an image. So I think this model may be able to be improved speed-wise if you use that, but I'm not sure. I think it would be interesting to look at changing the ODE solver that you use. But that is the paper. Yeah, it's cool to see this is the first model that is like really good at generating text from, or generating code from a diffusion model. So I'm excited to see if this model is as good as they kind of show it as and kind of says it's going to be. Yeah, code diffusion or code fusion.